Alright, so today we're going to wrap on the ideas of system software, and this is just the first section of the chapter. So we already know that in order to use a computing system we need both hardware and software. That's actually what makes a computing system, right? So how does that work? What happens when the computer is turned on nowadays? So what you have is the central processing unit, the memory, and all the the input-output system working together. And as you already know, the primary memory, is made out of two things, the ROM and the RAM. They have different purposes. They have different features. For example, ROM is read-only, right? And RAM is volatile. This is non-volatile. And this is where actually the programs run. I mean, the communication between the CPU and the RAM makes possible running programs, and that's why we have the address and the data bus here connecting both the CPU and the primary memory, right? So how does that work? When you turn the computer on, all the instructions that you have in ROM are loaded into RAM, and these instructions are the instructions that have the basic input-output system, which is known as the BIOS. And these are the instructions that check the different components of hardware and if they are running and if they are available for the computing process. You can also check things like the clock speed and all sorts of configurations for the hardware. And one important part of that is the bootstrap program. The bootstrap program is the one that is in charge of finding what's the secondary storage that is going to be used to load the operating system. So, as I said, first the ROM loads all the instructions in RAM, and those instructions are all about getting the system ready. And when that's ready, then the operating system needs to be loaded. And in the bootstrap is where you define where the operating system is. It's usually in the secondary storage, but it could be loaded from a CD or even a USB drive, even network. So in the bootstrap program is where you know where the operating system is residing. So the operating system is then, using the I/O system, is loaded into RAM, and then the operating system starts running. And the operating system is the program that is taking care of all the requests and all the handling of resources for the user. We're going to see that later on, but for the moment what you need to understand is that the basic input-output system is responsible for loading the operating system into memory and then being executed. So if you think about it, the operating system is always residing in a secondary storage, and then it's loaded when you put the computer on, when you start the computer. So the input-output system is good for that, for transferring information from different devices, like the hard disk, right, in this case. But that's not the only input-output device that you have. Well, the secondary storage it could be seen as an input-output system, but it's a storage device. But it uses the buses of communication with the main memory. Now, there are other input-output devices, like, for example, the keyboard, the mouse, the screen, the printer. They all use a little thing called the buffer. They have a buffer. It might be the same or different for each device, but this is what receives all the information that is coming there, and once it's ready, is sent through the bus to the CPU, well, mainly to the memory, and from the memory to the CPU. So that's kind of like how it works. So you load the basic input-output system, then the operating system is loaded, and then the computer is ready for requests, and it's ready to load other programs. Now, the operating system is a program, a bunch of instructions that are running there to handle different things for the user. One of the most important ones is the multi-programming that we have nowadays, where you can run multiple programs, not at the same time, but one after the other, and this operating system is handling how long each process is going into the computer, as you know, because we have already seen this scheduling algorithms, but that's just one of the things that it does. So it provides access to programs to the resources, memory and CPU, and input-output devices. And as you know, it handles interrupts, which are the mechanisms to stop one process and then go into the other. There are other things that it does, like for example, handling the communication with input-output devices. So it has the drivers that we know. Some of you might know what a driver is, but for example, to use a USB, to use printer, you need to install in the operating system a driver for the particular device that you're going to use. So the operating system handles that. And it's the one that allows the programs to use those resources, those input-output devices. It also handles the file system, so creation of files, folders, moving them from one to another place, and handling the user access for those folders and all that. That is all done by the operating system. One of the most important things that it provides to the user is the user interface. Now, there are many types of user interface. We have command line interface, we have graphic user interface, even voice or touch. It's handled by the operating system because it's the connection with the hardware and the user. We're going to see that later on. And it handles, as I said, the input-output devices, and it executes the programs and interacts with the programs. It provides an interface or a means of interaction between the user and the programs. And as I said, the file system, and it also provides a programming environment. So for high-level programming languages, it provides an environment to allow the programs, this layer of software, to connect to the hardware and to manipulate the hardware, just like I said, like the screen, printer, mouse, keyboard, and the different devices. You can manipulate those because the operating system provides, oh, there's a mistake here, provides interface between programs and the hardware, and that's called the application programming interface, the API. You might have heard that before. So just as an example, if you're the user who's using the computing system and you need, for example, you click in one button to open a file, that action that you sent to the CPU by the input system, which is the keyboard or the mouse, it's handled by the operating system and receives that what it's called a system call to manipulate the file system, and then go and talk to the driver of the disk and load that into memory and notify the program that the file is already accessed and all that. So it's handling all the interactions between hardware and software and the user. So the user interface is one big part of it, and that's what you could call the outer layer of the stack of software that you use when you're using a computer system. This could be the way that you could say that the user interacts with the hardware. So user starts by using inputs, using application programs, right? And these application programs may make system calls to the kernel or access utilities in the computer, like, I don't know, like disk fragmentation utilities, or I don't know what else. Yeah, the firewall, you know, and all those things that you kind of like use in a computer, but are not part of the kernel. The kernel is handling things that are more into every operating system, like a file system, as I said, networking, file access. This is file hierarchy. So it's talking about how to access folders and files and all that. This is permissions and access to memory and many other things that are handled by the kernel, which is like the closest to the hardware. So this is the layer of software that is controlling directly the hardware. And another way to see this, of how the kernel works, is like inside this kernel program there is a microkernel which is handling all the basic operations, and it has access to different functionalities or utilities in the operating system, like the ones I have already mentioned. One of the things that the kernel or the microkernel is handling is the access of the programs to the CPU. So this is what scheduling means. Is there are different levels of scheduling, but it's all related with how the programs are being accessed by the memory and the CPU. So we have a low level scheduling that or scheduling that it's handling how the different programs are being taken to the CPU. Now, a program that is running is called a process. So a process is a program or part of a program that is being run in or is ready to be executed by the CPU. So all the scheduling of these processes is made by the low-level scheduler. There's a medium level where the paging, which is the way you handle the memory in fixed sized slices, is handled and taken into the secondary storage when we are talking about virtual memory. We're going to talk about that later. And high level is just loading programs being stored in secondary storage and how to take those into RAM. So when you take a whole program, when you double click Word, for example, that program is being loaded into RAM, and that's being handled by the high level scheduler. So after it's running, then if you're using virtual memory, if there are many many programs running and you need more space in the primary memory, or you need to load a program that is probably higher in size than the actual memory that you have installed, then you need to use the virtual memory, and that's where the middle level goes. And then the lower level handles every single process and how they access the CPU. So a process goes, as you know, into five different stages. Once the first stage is called the start, and it's when the process control block is created. The process control block is just a space of memory where you have the information of the process that is going to be run and to be executed. And that's when it's taken from wherever it is into the primary memory and is ready to be processed by the CPU. So that moment is when you say that the process just started, because the PCB is created and is ready to be run. Then the dispatcher takes it from that point of creation into being ready for execution. Now, this is not when the program is running, but is when it's being handled by the scheduler to have access or to gain access to the CPU. Once that happens, when the scheduler assigns the time, it starts running, right? Now, from running state, it can either go to terminate if it's done. It can go to waiting if there is an interrupt, for example, for an I/O operation. Let's say that the process needed, I don't know, to bring something from the internet, and then this process go into waiting because that's a very slow process, bringing things from the internet. And once it's done, the scheduler receives another interrupt to say this program has already finished and it's ready to go back to the queue of scheduling for the CPU access. There's another way the processes that are running can go back to ready, and it's because the scheduler has decided to interrupt because it's using a preemptive way of providing access. We're going to see that in a few seconds. But that's also possible because there is an interrupt saying there is no more time for you in this running process. You need to be and wait in the ready line, the ready queue. One thing that I want to mention about the I/O operation is that this is necessary. The waiting state is necessary because the different devices that we have in the I/O system are very slow compared with the RAM, and very slow compared with the CPU execution. CPU execution is in the order of gigahertz, so that means that thousands of millions of operations are made in 1 second. But for example, the CPU, the keyboard, when a user is typing, it's like, I don't know, 10 bits per second. The speed of bits that you get, it's just like 10 bits per second. That's obviously a statistical calculation, but what it means is that you can now wait for the user to type a keyboard to continue doing what you're doing. And not even the screen is 50 VPS, and the secondary storage is usually in the order of megabits per second. Well, for this book, this 5 megabits per second is a normal thing, but with the new technologies of SSD drives and SATA drives, and SATA buses and M2 buses, these speeds have increased, getting closer to the gigabits per second. They're not yet, but some of them are. It's in the order of thousands or hundreds of megabits per second. So that's why these operations compared to the CPU are very slow. So they need to be taken into the waiting state because that takes too much to be waiting for the CPU to execute. So what you need to do is just, if that's going to take long, you just put the processing waiting and then you continue doing tasks with the CPU. Now, another way you can do that is to take a process and divide it in threads. Now, there are now technologies in computing where you can make use of different cores in the CPU, and then you divide your program in different threads, which are like different tasks of your program to be that are independent, and independent in the sense that they can be run at the same time. They don't need to wait one for the other. And then you make use of the different cores and you execute those, and it's making better use of the CPU access, of the CPU time. Now, the process control block that is created in the first stage has information that is required for the scheduler to handle that process. It has an ID for the process. It has information about when the process was executed the last time, and maybe how long it's going to take for it to finish, and maybe the type of operation that it is. Well, that would be a very advanced scheduler, but it's all the information that is required for the scheduler to handle that process. And the interrupt handling routine uses the information in the CPU block, in the PCB block, to assign time to the CPU. Now, there are two different ways in general that you can, different types of algorithms that you can use to assign time to the CPU or to schedule processes in the CPU. One of them is called preemptive, which means that you can stop any process at any given time, and non-preemptive means that you shouldn't stop a process that is being executed. Now, one general case, or one particular algorithm of a non-preemptive approach is the first come first served, which means that there is a queue where all the processes arrive, and depending on the position of their arrival, they're going to be executed. But if it's non-preemptive, then until the process number one is finished, then number two won't be able to access the CPU. So as you can imagine, that's very inefficient in terms of access to the CPU. But there can be algorithms that use this idea of a queue or first come first served for or as a combination with other preemptive algorithms, like, for example, the round robin. The round robin algorithm is supposed to give, let's say, the same amount of time for each process, or similar amounts of time for each process using the same queue. And that's kind of better, but it's not the best approach. The best approach, or the best algorithms, and the ones that are being used nowadays in CPU's designs, is to assign the time, for example, with the definition of a priority to the process, and to define different queues of different priorities, and so you can know where to assign those processes to CPU. So these queues of different priorities, for example, we could use round robin to go into each one of those queues. Let's say that this is the queue of processes. So we could say that we can do round robin just to go from to assign time to each queue, and then in each queue we have a priority, and then we can assign time given that that priority. Or we could say that, for example, this is priority 1, 2, and 3, and then we assign a time to the CPU, first to 1, then to 2, then to 3, and that this time is this priority is given larger times, and inside the queue we have first come first served. So that depends on the algorithm. What's important to understand here is that the priority may be given by using, for example, criteria as the total time that the process has been inside the CPU, or the remaining time that it has. I mean, how long that is it going to take to finish. It's just an estimation, but you could calculate that, and or how long it has been running. If there is a process that has been running too much, then maybe you should send it to the end of the queue. Or maybe the type of process. I mean, it might be an I/O bound or CPU bound. I/O bound means that most of the instructions are related with input-output devices. Or CPU bound means that it doesn't make much use of the input-output, but is more like instructions that are being executed. So those four ways are different approaches to define the estimation of priority. All right, I think that's the most important to talk about scheduling. Let's continue with the memory in the computer. So one of the other things that the operating system does is memory management. And what does it manage? It manages how the information or the programs are being loaded into the main memory for execution. Now, as you know, a memory is just space where you have data, and each slice of data is allocated in a particular address. Now, most of the tasks that the operating system or the microkernel is doing is allocating the different programs in memory for execution. So as you can imagine, there should be a space for the kernel, which is the whole operating system. And yeah, I mean, the kernel is handling how the kernel is being loaded there. I mean, when you load the operating system, the first thing you do is load all the kernel there, and then the operating system is checking that no one uses that space. And there are also instructions and data of the different programs that are being loaded into memory, and that is all handled by the operating system. Now, as you know, all the information that is stored in the computer is being kept in a secondary device, which is a non-volatile type of device, and it's a read and write type of device. So the information is always kept there, and then is taken into the primary memory when it's going to be executed. Now, how do you divide the memory to allocate all those programs? That are two main ways. One is the allocation of memory in a dynamic way, and that means that I'm going to start looking at the programs and the processes and see and check how big they are, and then I'm going to assign that space to the whole program or a segment of a program. So what it means is that I'm going to take care of how big the process is, and then I'm going to allocate that amount of memory to be taken by the program. Paging is a different approach, because instead of defining the space in memory based on the size of the process, what I do is I define fixed spaces in memory, let's say like pages of the same size in memory, and then I assign the programs to those spaces. So that makes easier the process of allocation. And that is actually what you need to do when you're thinking about virtual memory. Virtual memory is just creating virtual space for program allocation. It's virtual because it's not physically available in the primary memory, but it is expanded with space in the secondary memory. So if there's a program that is bigger than I don't know if it's a program, if the sum of the programs that we have, for example, it's 6 gigabytes, and the size of the memory that we have is 4 gigabytes, then we're going to be using at least 2 gigabytes of secondary memory, and with the use of the virtual memory. Now what it does is it provides a way to access memory locations that are not physically created. They are virtually created, and there is a map or information about where it actually is in the secondary on a table. So this is supposed to be primary, but there is a correspondence between the primary memory that doesn't exist, that is virtual, and the real space in secondary. What's the advantage of that? Well, you can, as I said, you can store large programs in memory, in primary memory, and if you make good decisions about what kind of instructions are being taken to the secondary and which instructions are being held in the primary memory, then you might make the multiprogramming faster. For example, if I take CPU bound operations taken into primary and I just keep the I/O operations in secondary, then it might run faster because the CPU is running this type of operations and is not waiting for I/O. Then the I/O is taken in the right moment to the primary memory to be executed. So what happens when you're doing this all the time, when you're taking information from secondary to primary and from primary to secondary? And if you keep doing that, the time is going to be expanded, and there's going to be an overhead of, a misuse of the resources in the CPU, and that's what you call disk trashing, which is trying to provide a faster way using virtual memory, but actually taking more time in the transferring of information between the primary and the secondary. So that's one of the problems or disadvantages, and the advantages are to have large programs and to have faster execution of multiprogramming. I think that's it that I have to say for this general terms of, or the summary of these two sections, and I'll make another video for the rest of the chapter for the next class. All right, take good care, bye bye.